Hello everyone. In this video we're going to be going over how to find the Laplace transform of a function by using the definition. So one of the functions that we might be given is one where it's given in a piecewise defined fashion. And a piecewise is just basically meaning that the function takes on different forms depending on the value of t. So if you notice, we have f of t is equal to t, which is just looking like a line, right, between 0 and 1. For 0 is equal to t, so that's including 0, and all the way up until 1, but not including 1. And the function f of t is 2. It's just a constant, so if you can imagine, you have a line from 0 to 1, say this is 0 to 1, and then from 1 and beyond we have a straight line. That is for t greater than 1. So you can tell it's indicated by this greater than or equals to 1 sign here. So basically we just apply the definition of the Laplace transform, which we have here. The Laplace of f of t, which is our function, is equal to this integral 0 to infinity e raised to the negative st times f of t dt. And so basically our work becomes just to apply the integral directly. Now in our case, the function changes, as we already said, it's a piecewise function, so it changes the form of the function based on the limit that we're looking at. So between 0 and 1, right, this first integral, we have the function as t. So that's why we have the limits from 0 to 1. And because the integral is a linear operation, we can actually just break up the integrals as we've done here. So we have from 0 to 1, it's that form, and then from 1 to infinity, which is the rest of the function, right? In our definition, we have all the way until infinity, and in our piecewise function, it's 2, f of t is 2 for t greater than or equal to 1, and that would indicate that we go all the way to infinity, which is designated here. So that's consistent with the definition. And of course, we see here that we have plugged in function as being 2. All right. So step 2 and step 3 are actually just evaluating each integral individually, because it's easier when we sort of break up these integrals here, find the value of each one and then just combine them at the end, and that'll actually be in step 4. So in step 2, we have to use the tabular integration method. So we do that process, which is illustrated here. Usually when we have an exponential and some sort of function t or t squared or t cubed, we can use the tabular integration method as opposed to the integration by parts, although you can also apply that. But in this case, the tabular method is fairly quickly performed, and then we end up with this function here. And it's important to see that this function is just a function of s's. So we went from a function of t to a function of s. And so basically that means we're going from the time domain to the s domain. All right. So in step 3, we just evaluate the other integral. So we're going from 1 to infinity, but remember our function is 2. So that's a little bit easier to evaluate because we can just move the 2 all the way in front of the integral, and we just integrate e raised to the negative st with respect to t here. And we find, after a few steps here, we find that we have this function of s again here. And then in step 4, we just simply combine the results of steps 2 and 3. So steps 2 and 3, and combine like terms. Most of the time you'll have some like terms. So if you're required to combine them, do that, and then you're going to end up with a function at the end of the day that's purely of s's. So you're going to have a s domain function, and that's the goal of the Laplace transform. So this is the Laplace transform of the function in red here.